All right, so today we're going to talk about Chapter 7, Probability and Samples, and the distribution of means. So it's going to be a continuation of what we discussed in Chapter 6. So for samples, population, and the distribution of sample means, the location of the score in a sample or in a population can be represented by a z-score. Researchers typically want to study those entire samples rather than a single score because the sample is going to tell us about the population. Samples provide an estimate of what we're saying about that population, and the procedure for transforming a sample mean is to a z-score. Sampling error sometimes occurs, and this occurs when we have an incomplete picture of the population. There's something wrong with it. A sample error is like a natural discrepancy, or the amount of error between a sample statistic and its corresponding population parameter. The area does not indicate that a mistake was made, but it tells us that these samples have variables and the two samples are very rarely identical to each other. So when we have those two separate samples, they're probably going to be different, even though they're taken from the same population. Whenever we have the distribution of sample means, we want to have that random sampling, and it's unlikely that those sample means would be the same. But when we distribute the sample means, it's the collection of those sample means and all the possible random samples of a particular size that can be obtained from that population. Distributions in earlier chapters were distributions of scores from samples, and this one is going to be about distribution of sample means. So a sample distribution is a distribution of statistics, not the scores. So the distribution of those sample means is a kind of a special to the population. It is obtained by selecting all the possible samples of a specific size from the population. The sample means should pile up around the population mean, and the distribution of sample means is approximately normal in shape. And the larger the sample size, the closer the sample means is to the overall population. So here's an example in Figure 7.2 of a frequency distribution histogram. If we had a population of 4 scores, this is what that histogram would look like. If we had the distribution of sample means, this is what that might look like, kind of similar to a normal distribution if we were to draw a line. And it's possible to determine exactly what the distribution of sample means looks like without taking hundreds or thousands of samples. The central limit theorem is used to help us specify the shape, the central tendency, the variability, and the variability of the distribution of sample means. This can apply to a population and a standard deviation. The distribution of sample means approaches a normal distribution as the number approaches infinity. This is the central limit theorem. And those distribution of sample means for the shapes will also matter. So if we take that standard deviation and we divide it by the square root of the number, then we can get the central limit theorem. The distribution of sample means is almost normally perfect in either of two conditions: if the population from which the samples are selected is a normal distribution, or if the number of scores in each sample is relatively large. At least 30 is considered relatively large. The mean of the distribution of samples is going to have a value that's equal to the mean of the population. And that mean of the distribution of sample means is called the expected value, or M. M is an unbiased statistic, and the expected value of the distribution of sample means is a population mean. We also have something called the standard error of M, and that refers to how well an individual sample mean represents the entire distribution. You have variability of a distribution of scores that's measured by the standard deviation, and variability of a distribution of sample means is measured by the standard deviation of the sample means, which also is called the standard error of mean. The standard error of mean is is the standard deviation of the distribution of sample means. And if it's large, it means it's widely scattered. This can also provide us with a measure of how much distance is expected on average. And then there's something called the law of large numbers, which says that whenever we have a large sample size, the more probable it is that the sample mean will be close to the population. Because of course, that population is very big. So we want a large number so it's more representative. Population variance occurs when the smaller the variance in the population, the more probable it is that the sample mean will be closer to the population. And if we look at sample figure 7.4, this shows you the relationship between the standard error and sample size. We can see that that standard error goes down with the more samples we have. As the sample sizes increase, there is less error between that mean and population. And here's figure 7.5, which shows us three different distributions. Part A shows the population of reading scores. Part B shows a sample of 16 reading scores. Part C shows the distribution of sample means for all possible samples. And note that that mean for the sample in Part B is one of thousands of sample means in the distribution shown. So here's our first learning check. We have that population mean of 60 with a standard deviation of 5, the distribution of sample means for the sample size, which is 4, that can be selected from the population would have an expected value of, do you think it would be A, B, C, or D? I'm going to give you a few moments to think of that. And the correct answer, if you got that, is 60, B. True or false, the shape of the distribution of sample means is always normal. True or false, the sample size increases. As the sample size increases, the value of the standard error decreases. And the correct answer is false and true. The shape is normal only if the population is normal, greater than 30. And the sample size is in the denominator of the equation. So as the number grows larger, the standard error is going to decrease. In section 7.3, it talks about z-scores and the probability of sample means. And the primary use of the distribution of sample means is to find the probability of selecting a sample with a specific mean. Proportions of the normal curve are used to represent those probabilities. A z-score for the sample mean is then computed. The sign will tell you whether the location is above or below the mean. The number tells the distance between the location and the mean in terms of the number of standard deviations, and follows the following z-score formula that you see on the screen. In figure 7.6, it tells us the distribution of sample means for a sample size of 16. Samples were selected from the normal population, as you can see. In figure 7.7, it shows us the middle 80% of the distribution of sample means. And whenever we have the standard error, there will usually be a discrepancy between the sample mean and the true population mean. That discrepancy is called a sampling error. The amount of sampling error can vary across samples, and the variability of sampling error is measured by the standard error of the mean. Here's an example in figure 7.8 of a typical distribution of sample means, very similar to a normal distribution. Each of the bars in the histogram represents the frequencies for different sample means. The curve for the normal distribution is superimposed on the histogram just so that you can see that it still follows the normal curve. In figure 7.9, it shows the distribution of sample means for A, B, and C obtained from a normal population. And then we can see the size of the standard error decreases as the sample size increases. So when we're going to report a standard error, journals can vary in how they refer to the standard error, but frequently use SE and SEM. This is often reported in a table along with the number and the mean and the different groups in the experiment. And they may also be added to a bar or line graph. Figure 7.10 shows us the different treatment groups for A and B. And figure 7.11 shows the mean number of mistakes for groups A and B on each of the trials they were in. When we look at inferential statistics, using the sample data as a basis for drawing general conclusions about populations can be made. That sample information is not a perfectly accurate reflection of the population due to sampling error. And the natural differences between the samples and populations introduce a degree of uncertainty and error into all inferential processes. So if we look at figure 7.12, it shows the structure of the research study described in example 7.7. The purpose of the study is to determine whether the treatment, a growth hormone, has an effect on the weight of rats. And then if we look at figure 7.13, we can see the distribution of sample means for the sample of 25 untreated rats. Let's go on and move to a learning check. A random sample with 16 scores is obtained from the population with a standard deviation of 16. If the sample mean is 58, the z-score corresponding to that sample mean should be what? I'll give you a few moments to think about it. A, B, C, or D. And the correct answer would be a z-score of 2. True or false? A sample mean with a z-score of 3 is fairly typical of a representative sample, and the mean of the sample is always equal to the population mean. Give you a few moments to think. And for both of these, they're going to be false. A z-score of 3 is an extreme, unlikely z-score, and individual samples will vary from the population. So hopefully that has aided in your understanding of the information presented in chapter 7.